University of Bridgeport. Wireless and Mobile Communications Laboratory. By Abir Lajlan. Under the supervision of Professor Khaled Alithi. In partial fulfillment of the requirements for the degree of Doctor of Philosophy in Computer Science and Engineering. Autonomous mobile robot navigation for planning collision-free path and static and dynamic environments. For the implementation we used Fezerbot robot from GHI Electronics. Fezerbot is a wheeled robot that has the following specifications. 2 motors, left motor and right motor. 4 AA battery holder. 6 gadgeteer sockets to connect modules with the robot. 1 USB client to connect to computer. And power source switch. 2 reflective sensors. 168 MHz 32-bit processor. 300 kilobytes flash memory. Since one single sensor is not capable of doing the task, employing multiple sensors rises in importance. The mobile robot used in this work utilizes 6 different modules, 2 infrared reflective sensors, 2 infrared distance measuring sensors, a serial camera and ultrasonic sensor. The experiments were executed in multiple scenarios, with different shapes of static and dynamic obstacles are placed in different locations around the robot. The experiments were carried out as follows. The experiment was conducted in a parquet floor, where opaque, translucent and transparent objects are placed around the robot. The experiment was performed to examine the ability of the infrared distance measuring sensors and ultrasonic sensor to detect different static obstacles. The experiment was tested in a dark area, so the ambient light does not affect the results. The experiment was run to examine how the ultrasonic sensor behaves for different light frequencies. This experiment was performed to determine the stability of detecting objects with moving camera. Here is the object detection flow. First, eliminate the effect of ego motion of the camera and extract a region of interest. 2 images of the same scene are linked, previous image and current image, so the effect of ego motion can be eliminated. Then, detect foreground object and perform video segmentation. The first frame of the video is used as the background where the intensity and color information for the background subtractions are considered to improve the accuracy of foreground segmentation. Next, calculate the foreground objects and connect foreground points as a blob. And finally, display detected object in image space. A single onboard camera has been mounted at the front of the robot to detect and track objects. Here is the video captured by moving camera. Optical flow computation involves estimation of image motion fields from temporal variations of spatial image data. Optical flow fields correspond to 2-dimensional projections of 3-dimensional movements of surfaces in a scene, either due to dynamic objects in the scene being imaged, or due to ego motion of the robotic platform on which the camera is placed. Optical flow estimation is used to characterize and quantify the motion of objects in a video stream, often for motion-based object detection and tracking systems. This is a selected frame from reference video. Then, the feature points is detected. The resulting binary masks from segmented image, where abandoned objects appear. The detection result where the image is cleaned with morphological filtering to clean up the image. The 4th experiment was conducted to examine the ability of detecting moving objects. The experiment is performed in an open area with 2 robots and some obstacles, where each robot is equipped with proximity sensors to detect each other and measure their relative distance. The proposed model is unlike two other reported algorithms. It guarantees a collision-free path from simple to critical environments including U and H-shaped obstacles. In the case of U-shaped obstacle, the robot senses the side walls, calculates the distance to front wall and steers inside. As the front wall is detected, the robot turns about 90 degrees to avoid it, and then, it turns about 90 degrees again when the side wall is detected. After avoiding a U-shaped obstacle, the robot continues its motion in that direction. These experiments were carried out to find optimal collision-free path ranging from simple to complex environments. The robot started from a given initial position and required to travel towards a predefined goal position following the shortest path. This is another environment where opaque and transparent obstacles are placed on the robot path. This is the 8th experiment where the robot is able to smoothly navigate through different types of obstacles and follow the optimal path from given configuration to goal configuration. The proposed model does not require prior information of the environment, as the decision is based on the current percepts captured by the sensors. In addition, there is no need for high memory and sophisticated processor, as a single microcontroller is enough to perform all computations. The proposed model is characterized by its low cost, low power consumption and its usefulness in avoiding obstacle and following the optimal path.